Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the hidden swarm of dust surrounding Three-Eye Atlas, a visitor from beyond our sun, trailing secrets older than Earth itself. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The comet arrives in late 2024, though no one sees it coming until it is already here. It moves through the inner solar system at 26 kilometers per second, faster than anything born within the sun's gravitational well. This speed is the signature of something that does not belong a hyperbolic orbit, a trajectory that curves once around our star and then continues outward forever. Astronomers catalog it as Three-Eye Atlas, the third confirmed interstellar object ever detected. The I stands for Interstellar. The Atlas refers to the automated survey telescope in Hawaii that first notices the faint smudge of light against the background stars. But the comet itself is not what lingers in the mind of researchers. It is the cloud around it, an envelope of dust so diffuse that no human eye could perceive it, even standing on the comet's surface. This swarm exists only as data, as measurements of scattered light and spectral lines, as models running on university servers in California and Chile and the Netherlands. The dust grains themselves are smaller than a red blood cell, suspended in vacuum, drifting outward from the nucleus at speeds too slow to measure directly. Only took 4.5 billion years to get here. The first hint comes from photometry, the careful measurement of how bright the comet appears over successive nights. It should brighten as it approaches the sun, following a predictable curve determined by distance and solar heating. But Three-Eye Atlas brightens erratically, flickering in ways that suggest something more complex than a simple icy body. The brightness changes not because the nucleus itself is flaring, but because the dust around it thickens and thins, a breathing cloud of particles that refracts and scatters sunlight in shifting patterns. Astronomers describe this as anomalous photometric behavior, which is the academic way of saying we did not expect this. By the time the comet reaches perihelion, its closest approach to the sun, it has developed a tail pointing away from the solar wind, as all comet tails do. But spectroscopic analysis reveals something unusual in the tail's composition. The dust is not fresh. It does not match the expected mix of silicates and organics that sublimate from a typical comet nucleus. Instead, the grains carry isotopic ratios that suggest formation in a stellar environment chemically distinct from our own. They are older than the sun, older than the planets, older than the molecular cloud that collapsed to form this entire solar system. The swarm is invisible to the naked eye, invisible even to most telescopes. It becomes real only through inference, through the way it absorbs certain wavelengths of ultraviolet light, through the polarization patterns it imposes on reflected sunlight, through the faint glow it produces in the infrared as solar radiation warms each grain to a few dozen degrees above absolute zero. Like measuring wind by watching leaves, there is a mystery embedded in the numbers. The dust distribution extends too far from the nucleus, forming a halo that stretches tens of thousands of kilometers in every direction. Standard cometary models predict that dust should remain relatively close to the source, bound by weak gravitational attraction and the slow outgassing of volatiles. But 3I Atlas sheds its dust like a dandelion, releasing seeds particles drifting away on forces too subtle to name, dispersing into an envelope that grows wider with each passing day. Some researchers propose that the dust predates the comet's arrival in our system. Perhaps it was already surrounding the object as it traveled through interstellar space, a cloud accumulated over millions of years of slow collisions with the tenuous medium between stars. Others suggest that the dust is freshly liberated, but from a nucleus with unusual structure, perhaps a loose aggregate of smaller bodies, or a comet with an unusually high dust-to-ice ratio. The data does not yet resolve the question. It simply sits there, a set of measurements waiting for a theory that fits. The comet will not return. Its orbit is open, a parabola that bends around the Sun and then continues outward toward the heliopause, the boundary where solar influence fades into the galactic background. In a few decades, 3I Atlas will be farther from the Sun than Voyager 1. In a few centuries, it will be invisible to every telescope humanity has yet built. The dust, meanwhile, disperses along the comet's trajectory, each grain following its own path through the outer solar system. Some will be pulled inward by Jupiter's gravity. Some will be pushed outward by radiation pressure. Most will simply continue drifting, a ribbon of ancient material threading through the Kuiper belt, slow as stone. Only the data remains, only the measurements, archived in astronomical databases, available to anyone with an internet connection, and the patience to parse CSV files of spectral flux and apparent magnitude. The swarm itself is already beyond Saturn, already fading into the darkness it came from, already gone. The dust is older than the Sun. This is not metaphor. This is isotopic measurement, mass spectrometry translated into dates and stellar environments. Each grain carries within its crystal lattice a record of where it formed, the temperature, the pressure, the chemical abundance of the molecular cloud that birthed it. And those conditions do not match the nebula that collapsed to form our solar system 4.56 billion years ago. The grains surrounding 3I Atlas come from somewhere else. Some other star's death, some other stellar nursery, light years away, where the ratio of oxygen 16 to oxygen 18 differs by a few parts per thousand, small differences, enough to tell a different story. Dust in space is not the household accumulation of skin cells and fabric fibers. It is mineral. It is glass. It is carbon arranged in lattices and chains, sometimes graphite, sometimes diamond, sometimes amorphous soot. The grains around 3I Atlas show signatures of silicate minerals, olivine and pyroxene, the same materials that form Earth's mantle and the surface of Mars. But the crystalline structure is different. The grains are smaller, more irregular, their surfaces etched by radiation exposure that measures in millions of years. They did not form in a planetary body. They condensed directly from gas, cooling in the outflow of a dying star or in the shock wave of a supernova expanding into the interstellar medium. Some grains contain pre-solar signatures, isotopic anomalies so extreme that they could only originate outside the solar system. These grains are found in meteorites sometimes, tiny inclusions embedded in the rock that fell to Earth, carrying messages from before the Sun existed. But those grains traveled here locked inside larger bodies, protected from erosion and contamination. The grains around 3I Atlas have traveled through open space, exposed to cosmic rays and interstellar hydrogen. Their surfaces slowly sputtered away by collisions with atoms moving at relativistic speeds. They should not have survived. Yet, here they are, drifting through our inner solar system, each one a fossil from a different epoch of galactic history. The question is not whether the dust is ancient. The question is how it remained attached to the comet. Interstellar space is not empty. It contains roughly 1 hydrogen atom per cubic centimeter, along with trace amounts of helium, carbon monoxide, and fine dust. An object moving through this medium at 26 kilometers per second experiences a headwind, not a viscous drag in the atmospheric sense, but a steady bombardment of particles that erodes surfaces and sweeps away loosely bound material. The dust around 3I Atlas should have been stripped away long ago, blown back along the comet's trajectory like smoke in a breeze. That it persists suggests either that the swarm is constantly replenished by sublimation from the nucleus, or that the dust is bound more tightly than current models predict. Another mystery filed away in the notes. Spectroscopic observations reveal organic compounds mixed with the silicates. Not life, nothing so complex, but carbon-based molecules, nonetheless polycyclic aromatic hydrocarbons, formaldehyde, methanol. Simple chains of carbon and hydrogen that form in the cold darkness between stars. These organics are common in space, found in molecular clouds and comets and the atmospheres of gas giants. What makes them notable here is their abundance and their state. The molecules surrounding 3I Atlas are partially processed, their bonds broken and reformed by exposure to ultraviolet radiation. They have spent time near a star, perhaps our Sun during this brief passage, or perhaps another star earlier in the comet's history. Like charred wood, evidence of fire, there is a poetic detail buried in the data that no one mentions in the formal papers. The dust grains, when analyzed for their rotation rates, spin slowly. Not the rapid tumbling expected from collisional dynamics, but a gentle, almost stately rotation, as if each grain was suspended in honey rather than vacuum. This may be an artifact of measurement, a bias in the way scattered light is interpreted, or it may indicate that the grains are larger and less spherical than assumed, their moments of inertia distributed in ways that damp angular momentum. The researchers note the anomaly and move on. There are only so many hours in a day, only so many grant proposals to write. The swarm contains, by conservative estimate, several million kilograms of material. This is calculated from the brightness of scattered light and assumptions about grain size and albedo. It could be 10 times more or 10 times less, depending on whether the grains are smooth or pitted, clustered or dispersed, coated in ice or bare silicate. Uncertainty is the constant companion of astronomy. Every measurement comes with error bars, every model with caveats. The dust is there, that much is certain. How much exactly, and arranged in what geometry, remains a question of ongoing refinement. What strikes the researchers, in the quiet moments between data runs, is the loneliness of it. This dust has traveled for millions of years through the space between stars, never illuminated, never warmed, moving in darkness so complete that the nearest light source might be a parsec away. And then, for a few brief months, it passes through the inner solar system, bathed in sunlight, visible to instruments on a single inhabited planet, before continuing back into the void. A few months out of millions of years. A statistical fluke that anyone was looking at all. The grains themselves do not change. They do not care about being observed. They continue their slow drift outward, following trajectories determined by forces too weak to feel the gentle push of solar photons, the faint tug of Jupiter's gravity, the imperceptible drag of the solar wind. In 1,000 years, the swarm will be twice as dispersed. In 10,000 years, the individual grains will be scattered across a volume larger than the solar system, indistinguishable from the background dust of the Kuiper belt. The information they carry will remain encoded in crystal lattices and isotopic ratios, waiting for no one. The physics of something so small operates under rules that do not apply to human-scale objects. A dust grain, 1 micron across roughly the wavelength of infrared light, has a mass measured in picograms, 15 zeros after the decimal point. At this scale, gravity becomes negligible. A grain at the distance of Earth's orbit feels the sun's gravitational pull, but the force is so weak that it takes months to alter the grain's trajectory by even a single degree. Meanwhile, other forces dominate. Radiation pressure. The momentum carried by photons striking the grain's surface pushes outward with a strength comparable to solar gravity. For the smallest grains, radiation pressure wins. They accelerate away from the sun, expelled from the solar system entirely, like seeds blown from a flower. The balance between gravity and radiation pressure depends on the grain's size and composition. Larger grains, 10 microns or more, are massive enough that gravity holds them. Smaller grains, a tenth of a micron, are blown away almost immediately. The swarm around 3I Atlas exists in the narrow window between these extremes grains, just large enough to linger, just small enough to drift. They orbit nothing. They fall toward nothing. They simply move through space, following trajectories shaped by forces measured in piconewtons, accelerations measured in fractions of a millimeter per second squared. It takes patience that only the universe possesses. There is also the solar wind, not wind in any terrestrial sense, but a stream of charged particles flowing outward from the sun's corona at 400 kilometers per second. Protons and electrons, mostly, with trace amounts of helium and heavier ions. These particles carry electric charge, and when they strike a dust grain, they transfer momentum. The effect is small, negligible for large objects, but for micron-sized grains, the cumulative impact over weeks and months can alter trajectories by measurable amounts. The grains acquire a slight electric charge themselves, becoming tiny dipoles embedded in the sun's magnetic field. They drift not in straight lines, but in gentle spirals, following field lines that curve and twist as the sun's magnetosphere rotates. Collisions, at this scale, are rare but not impossible. The space around 3I Atlas contains not only the comet's dust, but also the ambient population of interplanetary grains, debris from asteroids, fragments from other comets, micrometeorites that have drifted through the solar system for millennia. When two grains collide at relative speeds of a few meters per second, they do not bounce, they shatter, fragmenting into smaller pieces, or they stick together, fusing into aggregates held by electrostatic forces and van der Waals attraction. The outcome depends on the angle of impact, the composition of the grains, the temperature at the moment of contact. A collision that would be trivial for macroscopic objects, a pebble striking a stone, is catastrophic at this scale. Energy density matters more than total energy. Some grains sublimate slowly under solar heating, ice grains especially. Water ice begins to sublimate at temperatures above 150 Kelvin, which corresponds to the distance of the asteroid belt. Closer to the sun, the ice evaporates entirely, leaving behind only refractory materials, silicates, and organics that can withstand higher temperatures. The grains around 3I Atlas show evidence of both processes. Some are pure silicate, their surfaces smooth and glassy, suggesting prolonged exposure to heat. Others are fluffy aggregates, loosely bound clusters of smaller particles, their interiors still containing frozen volatiles protected from direct sunlight by outer layers of dust. These grains outgas slowly, releasing molecules of water and carbon monoxide that contribute to the comet's faint coma, the diffuse atmosphere that makes the object visible in the first place. The swarm is not static. It evolves. As the comet moves away from the sun, the grains cool, their sublimation rates dropping exponentially with decreasing temperature. By the time 3I Atlas crosses the orbit of Jupiter, most outgassing has ceased. The grains that remain are the survivors, the ones large enough or refractory enough to withstand solar heating. The ones that happen to be shielded by other grains or ejected from the nucleus at just the right velocity to escape into stable orbits. Natural selection applied to dust. There is a mystery in the distribution. Observers measure the dust density at various distances from the nucleus, constructing a radial profile that should follow predictable patterns based on ejection velocity and gravitational influence. But the profile is flatter than expected. The density decreases too slowly with distance, as if the grains are being replenished from some reservoir, or as if they are bound by a force not accounted for in the models. Some researchers speculate about electrostatic effects, about charge separation creating weak attractive forces between grains. Others suggest that the nucleus itself is fragmenting slowly, releasing large clumps of dust that disperse over time. The data does not yet distinguish between these possibilities. It sits in tables and graphs, waiting for someone to notice the pattern that makes sense of it all. The grains also spin. Every object spins, given enough time and enough collisions to impart angular momentum, but the spin rates measured for the dust around 3I Atlas are puzzling. They are too slow, orders of magnitude slower than what collision dynamics predict. A micron-sized grain struck by a molecule of the solar wind should tumble rapidly, completing thousands of rotations per second. Instead, the grains rotate languidly, as if damped by some invisible medium. One hypothesis is that the grains are not solid, but porous, their interiors filled with empty space that dissipates rotational energy through internal friction. Another hypothesis is that the grains are coated in ice, and as the ice sublimates, it carries away angular momentum, slowing the spin. Both explanations are plausible. Neither is confirmed. Measuring these grains requires instruments that do not quite exist yet. The best current technology, space-based telescopes with adaptive optics and high-resolution spectrographs, can detect the swarm's presence and infer its gross properties. But individual grains remain invisible. They can be studied only in aggregate, as statistical populations, their properties averaged over millions of particles. It is like trying to understand a forest by measuring the total mass of leaves without ever seeing a single tree. The information is there, encoded in the light, but extracting it requires assumptions and models and a willingness to accept uncertainty as a permanent condition. Still, the measurements continue. Observatories around the world and in orbit track the fading comet, recording spectra and brightness variations as it recedes into the outer solar system. Each data point refines the model slightly. Each observation narrows the range of possibilities. Slowly, over years and decades, a picture emerges not complete, never complete, but clearer than before. The dust around 3I Atlas drifts onward, indifferent to scrutiny, following paths determined by physics too subtle to name. The swarm is discovered by accident, which is how most things in astronomy are discovered. Astronomers are looking for the comet itself, tracking its motion across the sky when they notice something odd in the data. The comet's brightness fluctuates more than it should, not the regular variations caused by a rotating nucleus, but irregular changes that suggest something else is happening, something in the space around the comet, not the comet itself. This is October 2024. The comet is still 3 astronomical units from the Sun, far enough that most volatiles remain frozen, close enough that solar heating has begun to liberate dust from the surface. The first observer to note the anomaly is an astronomer in South Africa, working a night shift at a robotic observatory in the Karoo Desert. She is running a standard photometry routine, measuring the brightness of known objects to calibrate the telescope's detectors. 3i Atlas is on the list because it is new and because interstellar objects are always worth monitoring. The brightness measurement comes back higher than predicted by the standard cometary model. She checks the calibration, she checks the sky conditions. She reruns the observation an hour later. The brightness has changed again, but not in the direction the model predicts. She makes a note in the observation log and moves on to the next target. There are 300 objects to measure before dawn. The note sits in the database for 2 weeks before anyone else looks at it. Then a graduate student in California, mining archived data for a different project, notices the discrepancy. He pulls up additional observations from other telescopes, archives from Chile, from Hawaii, from Spain. All show the same pattern. The comet's brightness varies on timescales of hours to days, sometimes brightening by 10%, sometimes dimming by the same amount. The variations do not correlate with the comet's distance from the Sun. They do not correlate with its rotation period, which has been estimated at around 16 hours. They correlate with nothing obvious. The breakthrough comes from spectroscopy. When astronomers split the comet's light into its component wavelengths, they see not just the reflected sunlight from the nucleus, but also scattered light from the surrounding environment. And this scattered light has a signature, a subtle shift in polarization, a slight reddening at certain wavelengths that indicates the presence of dust grains. Not the large particles that form the comet's visible tail, but smaller grains, micron-sized, dispersed in a diffuse cloud around the nucleus. The cloud's density varies with time, thickening and thinning in response to outgassing events and solar heating. When the cloud is dense, the comet appears brighter. When it disperses, the brightness drops. The comet itself has not changed, only the veil around it. This realization takes 3 months of analysis. By then, 3i Atlas has passed perihelion and is moving outward, beyond the orbit of Mars. The swarm is still there, still detectable, but fading as the comet recedes. Observing time on major telescopes is precious, allocated months in advance through competitive proposals. By the time a team secures time to study the swarm in detail, the comet is already dim, requiring long exposures and careful background subtraction to separate its faint glow from the scattered light of the Milky Way. The observations reveal structure. The swarm is not uniform. It is denser in some directions than others, forming asymmetric lobes and streamers that extend tens of thousands of kilometers from the nucleus. These structures suggest that the dust is being ejected preferentially from certain regions of the comet's surface, perhaps active vents or exposed patches of volatile rich material. Or perhaps the structures reflect the influence of the solar wind, which pushes the dust into patterns determined by the comet's orientation and velocity. The data does not resolve the question. It only shows that the swarm has shape, has geometry, has features that demand explanation. One of the subtler discoveries comes from measuring how the swarm scatters light at different wavelengths. Dust grains scatter blue light more efficiently than red light if they are small enough, comparable in size to the wavelength itself. This is Rayleigh scattering, the same phenomenon that makes Earth's sky blue, but the dust around 3i Atlas scatters red light more efficiently than blue. This indicates that most grains are larger than a micron, perhaps several microns across. Too large for Rayleigh scattering, but still small enough to be pushed by radiation pressure. The exact size distribution can be inferred from the scattering spectrum. Though the process involves fitting complex models to noisy data and accepting uncertainties of 50% or more. Good enough for astronomy, not good enough for engineering. There is also the question of composition. Spectroscopy reveals absorption features consistent with silicate minerals, olivine and pyroxene, but the features are broader and shallower than expected for pure crystalline grains. This suggests that the grains are either amorphous, lacking the regular crystal structure of minerals formed in high-temperature environments, or that they are coated in some material that masks the underlying silicate signature. Ice is one possibility. Organic tars are another. Both are common in comets. Both would broaden spectral features in the observed way. Distinguishing between them requires observations at wavelengths not easily accessible from ground-based telescopes mid-infrared, where ice and organics have distinct absorption bands. But those observations require space telescopes, and space telescopes have waiting lists measured in years. The astronomers publish their findings in a paper that runs to 23 pages, including figures and supplementary material. The abstract is 200 words, carefully worded to emphasize the novelty of the observations while acknowledging the limitations of the data. The paper is accepted after peer review, with minor revisions. It appears in a journal that specializes in planetary science, where it will be read by a few hundred specialists and cited by perhaps 20 subsequent papers over the next decade. This is the normal pace of discovery. Slow accumulation of detail, incremental refinement of understanding. The swarm itself, meanwhile, continues to disperse, indifferent to publication schedules and citation metrics. What strikes the observers in the months following the discovery is how close they came to missing it entirely. If the photometry had been slightly less precise, if the spectroscopic observations had been scheduled a few weeks later, if the graduate student had not happened to query that particular subset of the archive, the swarm would have remained invisible, a feature too subtle to detect in routine observations, too transient to catch with targeted campaigns. Only luck and the sheer volume of data collected by automated surveys made the discovery possible. Only chance that anyone was looking at the right moment. By the time the paper is published, 3I Atlas is beyond the orbit of Jupiter, faint enough that only the largest telescopes can detect it. The swarm is still there, presumably, still dispersing according to the laws of physics, but it is no longer observable. The data that exists is all the data there will ever be, a few months of measurements, archived on servers, available to anyone who wants to reanalyze them. The comet continues outward. The swarm continues its slow dissolution. The universe does not pause for human curiosity. The dust distribution defies the standard model. This is the polite way researchers phrase it in their papers. The harsher phrasing, used in private emails and late-night conversations, is that the swarm makes no sense. Cometary dust should follow predictable patterns, determined by ejection velocity, solar radiation pressure, and the comet's motion through space. Near the nucleus, the density should be high. Farther out, it should decline according to an inverse square law, thinning as the grains disperse into a larger volume. The tail should point away from the sun, shaped by the solar wind. All of this is well understood, validated by decades of observations of short-period comets like Halley and Encke, but the swarm around 3I Atlas does not behave this way. The density profile is too flat. Measurements taken at 10,000 kilometers from the nucleus show nearly the same dust density as measurements taken at 50,000 kilometers. The tail exists, pointing in the expected direction, but it is broader and more diffuse than models predict, and it contains substructure filaments and knots that appear and fade over timescales of days. The overall impression is of a cloud that is too large, too dispersed, too persistent to be explained by recent ejection from the nucleus alone. One hypothesis is that the dust is ancient. Perhaps it has been surrounding the comet for millions of years, accumulated during the object's long journey through interstellar space. In this scenario, the swarm is not freshly created, but merely illuminated by the sun's proximity, made visible for the first time as the comet passes through the inner solar system. The grains would be interstellar dust, swept up by the comet as it traveled, adhering to the nucleus through electrostatic forces or weak gravitational attraction. This would explain the extended distribution and the unusual composition. But it creates a new problem. How does the dust remain bound? Interstellar grains are small and light, easily stripped away by the ram pressure of the interstellar medium. A comet moving at 26 kilometers per second should be shedding dust, not accumulating it. Another hypothesis focuses on the comet's structure. Perhaps 3I Atlas is not a single solid body, but a loose aggregate, a rubble pile, in the technical terminology. A collection of smaller fragments held together by weak gravity and friction, with large void spaces between components. Such a structure would be fragile, prone to slow disintegration under the stress of solar heating and tidal forces. As the comet warms, internal volatiles sublimate, creating pressure that pushes fragments apart. The comet does not break catastrophically, but rather erodes gently, releasing dust not from its surface, but from its interior, from reservoirs that have remained frozen and protected until now. This would produce a more extended dust distribution, as grains are released over a longer time scale and from a larger effective volume. There is also the possibility that the swarm is not dust at all, or not entirely dust. Some spectroscopic features suggest the presence of larger particles, millimeter-sized or even centimeter-sized, too small to see individually, but collectively contributing to the scattered light. These particles would behave differently than micron-sized grains, less affected by radiation pressure, more influenced by gravity and ejection velocity. They would form a distinct population, overlapping with the smaller grains, but following different trajectories. Sorting out the contributions of different particle sizes requires careful modeling and observations at multiple wavelengths. The data available for 3I Atlas is sufficient to hint at this complexity, but not to resolve it fully. A lesser-known detail emerges from polarimetry, the measurement of how light's polarization changes as it scatters off the dust. Natural sunlight is unpolarized, vibrating in all directions perpendicular to its direction of travel. But when light scatters off a dust grain, it becomes partially polarized, vibrating preferentially in one plane. The degree of polarization depends on the scattering angle and the properties of the grain, its size, shape, and composition. For the swarm around 3I Atlas, the polarization is weaker than expected, suggesting that the grains are either larger than assumed or irregularly shaped, or that they are clumped into aggregates rather than dispersed as individual particles. Polarimetry is a subtle art. Few observatories have the instruments to measure it accurately. Fewer still have the time to devote to a single fading comet. The swarm also shows spectral features that do not match any single material. The infrared spectrum contains broad absorption bands consistent with silicates, but also narrow features that might indicate crystalline water ice or organic compounds. The visible spectrum shows a slight reddening, a color shift toward longer wavelengths that could be caused by organic tars coating the grains. The ultraviolet spectrum, captured by a space telescope during a brief observing window, reveals absorption by polycyclic aromatic hydrocarbons, carbon rings that form in the outflows of dying stars and are common in the interstellar medium. Each spectral region tells a slightly different story, as if the swarm is not a single population of grains, but a mixture of materials from different sources and different epochs. This heterogeneity is not unusual for comets. Cometary nuclei are believed to be primitive bodies, agglomerations of material that formed in the outer solar system 4.5 billion years ago and have remained largely unaltered since. They contain a mix of ice, rock, and organic compounds, preserved in the cold darkness beyond Neptune's orbit. When a comet is perturbed into the inner solar system, solar heating releases this mixture, and the dust reflects the diversity of its source. But 3i Atlas is not from the outer solar system. It formed around a different star, in a molecular cloud with a different chemical composition. The heterogeneity in its dust suggests that even outside our solar system, the process of comet formation involves mixing materials from diverse sources, stellar outflows, supernova ejecta, pre-existing interstellar grains. Everywhere, it seems, is chaos and aggregation. The researchers run numerical simulations, attempting to reproduce the observed dust distribution with different assumptions about ejection velocity, grain size, and nucleus structure. Some simulations come close, matching the overall shape of the swarm but failing to capture the fine details. Others produce distributions that look nothing like the observations, ruling out certain scenarios. The process is iterative. Adjust the parameters. Rerun the simulation. Compare to data. Repeat. After months of this, a rough consensus emerges. The swarm is probably a combination of recent ejection and older material, with contributions from both surface outgassing and internal fragmentation. The exact proportions remain uncertain. The data permits a range of interpretations, all of them plausible, none of them definitive. What no one mentions, except in passing, is the aesthetic satisfaction of seeing something unexpected. Science is often portrayed as the confirmation of predictions, the matching of theory to observation. But the deeper pleasure comes from anomalies, from observations that do not fit, that demand new thinking or at least a willingness to sit with uncertainty. The swarm around 3i Atlas is such an anomaly. It behaves in ways that current models do not fully explain. It exists at the edge of what instruments can detect. It will be gone soon, beyond reach, leaving only questions and a few gigabytes of archived data. Only took a few million years to deliver this mystery to our doorstep. Comets, remember, this is not sentiment, but chemistry. Every molecule frozen into a cometary nucleus carries information about the conditions where it formed, the temperature, the density, the radiation environment of the molecular cloud that birthed the comet's parent star. When astronomers analyze the composition of cometary ice, they are reading a record written in isotopes and molecular ratios, a text that describes stellar neighborhoods that no longer exist, clouds that dispersed billions of years ago, regions of space that will never be visited by any probe humanity might build. The water in 3i Atlas has a deuterium to hydrogen ratio that differs from Earth's oceans. Deuterium is heavy hydrogen, an isotope with an extra neutron in its nucleus. It forms in the same nuclear reactions that produce ordinary hydrogen, but in slightly different proportions depending on temperature and pressure. In cold molecular clouds, deuterium becomes enriched in water molecules through chemical reactions that favor the heavier isotope. The exact enrichment depends on the cloud's temperature. Colder clouds produce more deuterium-rich water. By measuring the D to H ratio in cometary water, astronomers can infer the temperature of the cloud where the comet's ice originally condensed. For 3i Atlas, the ratio is higher than most solar system comets, suggesting formation in a colder environment. Perhaps the molecular cloud that surrounded its parent star was denser and more shielded from external heating. Perhaps the comet formed farther from its star, in regions where temperatures hovered just a few degrees above absolute zero. The measurement is difficult. requiring high-resolution spectroscopy to distinguish the faint absorption line of deuterated water from the much stronger line of ordinary water. The signal is buried in noise, extracted through careful data processing and statistical analysis. The uncertainty is large 30%, perhaps 40%. But the central value is clear enough this water froze under conditions different from those that prevailed in our solar system's formation. There are also organic molecules, carbon-based compounds that form in space through slow chemistry driven by ultraviolet radiation and cosmic rays. Methanol, formaldehyde, hydrogen cyanide, acetylene. Simple molecules, 2 or 3 atoms linked together, but complex enough to hint at the richness of interstellar chemistry. Some of these molecules are detected through their emission lines, as solar heating causes them to sublimate and fluoresce. Others are inferred from the infrared spectrum, from broad absorption features that match laboratory measurements of organic ices. The abundances relative to water vary from comet to comet, reflecting differences in formation conditions. For 3I Atlas, the methanol abundance is lower than average. The formaldehyde abundance is higher. These are not dramatic differences. They are the small variations that distinguish one stellar environment from another. The dust itself carries chemical information. Silicate grains contain trace elements, magnesium, iron, aluminum in ratios that depend on the composition of the gas from which they condensed. Grains formed in oxygen-rich environments have more magnesium. Grains formed near massive stars, which produce large amounts of heavy elements through nucleosynthesis, have higher iron content. The trace element ratios in the dust around 3I Atlas suggest formation in a region enriched in heavy elements, perhaps near a cluster of massive stars or in the aftermath of a supernova explosion. But the signal is weak, the measurements are indirect, and the uncertainties are substantial. The claim is made cautiously, with appropriate qualifiers and caveats. There is a mystery in the nitrogen. Cometary nuclei contain nitrogen in several forms: molecular nitrogen, ammonia, hydrogen cyanide. The ratio of nitrogen-15 to nitrogen-14 varies depending on the chemical pathways by which nitrogen was incorporated into volatile molecules. In the solar system, this ratio is well measured, consistent across comets and asteroids and the atmospheres of planets. But in 3I Atlas, the ratio appears different higher, by a margin that exceeds measurement uncertainty. This suggests that the nitrogen in this comet was processed through different chemical reactions, perhaps in a cloud with a different ionization state or a different exposure to cosmic rays. Or perhaps the measurement is simply wrong, biased by some unaccounted systematic error. The researchers flag the result as tentative, worth following up if another interstellar comet is discovered. The organic compounds also show signs of processing. They are not pristine molecules condensed directly from gas, but rather products of secondary chemistry reactions that occurred after the initial formation, driven by radiation or heat. Some molecules show evidence of bond breaking and reforming, of molecular fragments recombining into new structures. This processing could have occurred during the comet's long journey through interstellar space, as cosmic rays bombarded the nucleus and slowly altered its chemistry. Or it could have occurred recently, as solar ultraviolet light broke apart molecules on the comet's surface and allowed them to react with each other. The spectral features do not distinguish between these possibilities. They only show that the organics have a history, that they have been changed by forces and time. What comets remember, ultimately, is not specific events, but conditions. They do not record the explosion of a particular supernova or the birth of a particular star. They record temperatures and densities and radiation fluxes, the average properties of the environments through which they have passed. This information is valuable precisely because it is generic. It describes not one place, but a type of place, not one moment, but an epoch. The chemistry of 3I Atlas tells us that interstellar space, at least in the region where this comet formed, resembles in many ways the outer edges of our own solar system, cold, dark, rich in simple molecules and fine dust. But it differs in the details, in the isotopic ratios and trace element abundances that mark it as foreign. The memory is imperfect. Cometary ice sublimates, carrying away the most volatile molecules and leaving behind a residue enriched in less volatile components. Solar heating alters the surface composition, driving off water and leaving behind a crust of organic material and dust. Cosmic rays penetrate the nucleus, breaking chemical bonds and creating new molecules through radiolysis. Over millions of years, the original composition is overwritten, modified, obscured. What remains is a palimpsest, the original text still legible but faint, visible only through careful reconstruction and analysis. And yet the information persists. Locked in crystal lattices, embedded in isotopic ratios, encoded in the structure of complex organic molecules. The dust grains surrounding 3I Atlas carry with them a record of their birth, written in the language of physics and chemistry, decipherable by instruments and minds capable of asking the right questions. The comet does not know what it remembers. It simply is, moving through space, gradually dispersing, gradually eroding, its message fading with time, but not yet lost, not yet silent. Between stars, dust drifts in near-total darkness. The nearest light source might be a parsec away 3.26 light-years, 30 trillion kilometers, a distance that reduces even the brightest stars to faint points indistinguishable from the cosmic background. At this distance, starlight delivers less than a trillionth of the energy flux that bathes Earth's surface. It is not enough to warm a dust grain by even a fraction of a degree. The grains float at temperatures just a few degrees above absolute zero, their thermal energy barely sufficient to vibrate the atoms in their crystal lattices. They radiate in the far infrared, wavelengths measured in hundreds of microns, photons so weak that they carry almost no information, almost no energy. The interstellar medium is not empty, but it is sparse. 1 hydrogen atom per cubic centimeter, on average. In denser regions, molecular clouds where stars are born, the density might rise to 1,000 atoms per cubic centimeter. In the voids between spiral arms, the density drops to 1/100th of an atom per cubic centimeter. For comparison, the air at sea level on Earth contains 10 billion trillion molecules per cubic centimeter. The interstellar medium is vacuum by any terrestrial standard, emptier than the best laboratory chambers, emptier than the space between electrons in an atom, and yet, across the immense volumes of galactic space, even this tenuous gas contains mass. The Milky Way's interstellar medium masses billions of times the Sun, spread thin, invisible, present nonetheless. Dust grains moving through this medium collide occasionally with hydrogen atoms. The collisions are gentle, almost imperceptible. A hydrogen atom masses 1.67 times 10 to the negative 27 kilograms. A micron-sized dust grain masses 1 trillion times more. The collision imparts momentum, but so little that it would take millions of collisions to alter the grain's velocity by even a millimeter per second. Over geological timescales, however, these collisions accumulate. A grain traveling through the interstellar medium for 1 million years experiences enough collisions to slow its motion, to erode its surface, to gradually sputter away its outer layers, atom by atom. There is also radiation, though not from any nearby star. The galaxy is filled with low-energy photons, the cosmic microwave background, relic radiation from the Big Bang, now cooled to just under 3 Kelvin. These photons are everywhere, isotropic, unavoidable. They do not heat dust grains significantly, but they do exert pressure, the same radiation pressure that pushes cometary dust away from the Sun. In interstellar space, where starlight is negligible, the microwave background becomes the dominant source of photon momentum. The effect is tiny, measured in femtonewtons, but it is constant, unrelenting. Over millions of years, it shapes the motion of the smallest grains, nudging them in directions determined by the local variations in the background's temperature and intensity. Cosmic rays also penetrate the medium. These are not rays, but particles, protons and heavier nuclei accelerated to near-light speeds by supernovae and other violent events. They carry enormous energy, enough to shatter atomic nuclei and create cascades of secondary particles when they strike matter. A cosmic ray impacting a dust grain does not destroy the grain, but it does damage the crystal structure, breaking chemical bonds and creating defects in the lattice. Over time, this damage accumulates, amorphizing crystalline grains, making them less ordered, more chaotic in structure. The grains darken, their surfaces becoming rough and pitted, their reflectivity decreasing. They become harder to see even when illuminated. The magnetic field of the galaxy threads through the interstellar medium, weak but pervasive. Charged particles, ions, and electrons spiral along field lines, trapped in helical orbits. Dust grains, though electrically neutral on average, acquire small charges through collisions with ions and through photoelectric emission when struck by ultraviolet photons. Once charged, the grains interact with the magnetic field, experiencing forces that depend on their velocity and the field's geometry. These forces are weak, insufficient to bind the grains to field lines, but they are enough to influence the grain's motion on long time scales, to create patterns and alignments in the dust's distribution that mirror the structure of the magnetic field itself. In this environment, 3I Atlas traveled for millions of years. The exact duration is unknown, dependent on the comet's origin and the distance it has covered. If it formed in a star system 10 parsecs away, the journey at 26 kilometers per second would have taken roughly 100,000 years. If it came from farther, 100 parsecs, the journey stretches to 10 million years. During this time, the comet experienced nothing, no seasons, no day or night, no external change except the slow, imperceptible erosion of its surface by cosmic rays and the rare impact of interstellar grains. It drifted through a darkness so complete that the concept of visibility loses meaning. There was no light to see by, no observer to see, only motion through void. The comet's trajectory was not straight. Gravitational perturbations from passing stars deflected it slightly, bending its path by fractions of a degree. A close pass by a massive star within a light year or so could alter the trajectory more significantly, slowing or accelerating the comet, changing its direction by tens of degrees. But such encounters are rare. Most of the time, the comet moved in a nearly straight line, its velocity constant, its orientation fixed by whatever forces shaped its spin when it was ejected from its parent system. The spin rate, too, remains nearly constant. There is no air resistance to slow it, no tidal forces to alter it. The comet rotates at the same rate now as it did a million years ago. A clock wound once and never reset. There is a quiet irony in this isolation. The interstellar medium, though sparse, is where most of the galaxy's matter resides. Stars and planets contain only a small fraction of the total mass. The rest is gas and dust, spread through volumes so vast that their combined mass dwarfs the stellar population. And yet this matter is invisible, undetectable except through its effects on starlight and its emission at radio wavelengths. It is the dark matter of classical astronomy, present but unseen, felt only indirectly. A comet traveling through this medium is surrounded by matter but experiences solitude more profound than any isolation possible within a planetary system, at least near a star. There is light, at least in orbit. There is something to orbit. In interstellar space, there is only drift. The dust grains surrounding the comet share this isolation. Each grain follows its own trajectory, determined by the forces acting on it when it was ejected or accumulated. Some grains drift ahead of the nucleus, accelerated by radiation pressure from the distant stars. Others lag behind, slowed by collisions with interstellar hydrogen. The swarm disperses gradually, expanding as the grains separate, thinning as they spread into larger volumes. In a million years, the grains will be scattered across a region light years across, indistinguishable from the background population of interstellar dust. The comet will have passed, leaving no trace except the faint enrichment of dust density along its trajectory, a signal too weak to measure, too transient to persist. And yet the silence is not absolute. Radio telescopes on Earth detect the interstellar medium through the emission of neutral hydrogen at 21 centimeters, a wavelength corresponding to a transition in the hydrogen atom's spin state. This emission is faint, requiring large antennas and long integration times to detect, but it maps the medium's structure, revealing clouds and filaments and voids, the architecture of the space between stars. The comet passes through this structure, a small body moving through a medium that extends across the galaxy, connecting star systems that will never interact gravitationally, never exchange light in any meaningful sense. The comet is alone, but not separate. It is part of the medium, another particle drifting in the cosmic dark. Measuring the invisible requires inference and indirection. The dust grains around 3I Atlas are too small to photograph, too faint to resolve individually, too distant to sample directly. They exist only as light-scattered sunlight, absorbed starlight, thermal emission in the infrared. Astronomers point telescopes at the comet and record the photons that arrive, then work backward from these photons to reconstruct the properties of the grains that emitted or scattered them. It is an inverse problem, mathematically ill-posed, admitting many solutions for any given dataset. The challenge is to find the solution that is both consistent with observations and physically plausible. Spectroscopy is the primary tool. When light passes through or reflects off a dust grain, certain wavelengths are absorbed or scattered more efficiently than others. The pattern of absorption and scattering depends on the grain's composition. Silicates absorb strongly in the mid-infrared around 10 microns. Water ice absorbs at 3 microns. Organic compounds produce broad features across the near-infrared. By measuring the comet's brightness at many wavelengths, astronomers construct a spectrum, a graph of intensity versus wavelength. The spectrum contains information about what materials are present, though extracting that information requires comparing observations to laboratory measurements of candidate materials and to theoretical models of light-matter interaction. The spectrum of 3I Atlas shows broad absorption features centered near 10 microns, consistent with silicate dust, but the features are broader and shallower than laboratory spectra of pure silicate minerals, suggesting that the grains are not pure. They might be amorphous rather than crystalline, their atoms arranged randomly rather than in regular lattices. Or they might be coated with ice or organics, materials that do not have strong spectral features themselves, but that dilute the signatures of the underlying silicates. Distinguishing between these possibilities requires fitting models to the data, adjusting parameters until the predicted spectrum matches the observed one. The best fit model gives an amorphous silicate core with a coating of organic material, but the fit is not perfect. Residuals remain. Small discrepancies between model and observation that hint at additional complexity not captured by the simple two-component model. Polarimetry adds another dimension of information. Light scattered by dust grains becomes polarized, meaning that the electric field oscillates preferentially in one direction rather than randomly in all directions. The degree of polarization depends on the scattering angle, the angle between the incoming sunlight, the grain, and the observer, and on the grain's properties. Spherical grains produce less polarization than elongated grains. Large grains produce different polarization patterns than small grains. By measuring the polarization at different wavelengths and different scattering angles, astronomers constrain the size distribution and shape of the grains. For the swarm around 3I Atlas, the polarization is measured at just 2 wavelengths visible and near infrared, and at a limited range of scattering angles determined by the comet's geometry and the timing of observations. The data points are few. The error bars are large, but the pattern is clear enough the grains are elongated, with aspect ratios of roughly 2:1, and they are aligned to some degree, their long axes preferentially perpendicular to the scattering plane. This alignment is unexpected. In most cometary dust clouds, grains tumble randomly, producing no net alignment. The alignment in 3I Atlas suggests that the grains are spinning and that their spin axes are not randomly oriented. Perhaps the grains were ejected from the nucleus with some preferred orientation, or perhaps they have been torqued by radiation pressure or gas drag into aligned configurations. The data does not distinguish between these mechanisms. It only shows that the alignment exists. Thermal emission provides yet another constraint. Dust grains absorb sunlight and re-radiate the energy as heat, emitting infrared photons with a spectrum that depends on the grain's temperature and emissivity. The temperature depends on the grain's distance from the sun and its size. Smaller grains, with higher surface area to volume ratios, are warmer than larger grains at the same distance. By measuring the infrared emission at multiple wavelengths, astronomers infer the temperature distribution of the grains, which in turn constrains their size distribution. For 3I Atlas, the thermal emission is faint, detectable only by space-based infrared telescopes with large apertures and sensitive detectors. The observations are made during a narrow window when the comet is bright enough and positioned favorably. The data shows emission peaking near 50 microns, corresponding to grain temperatures of around 60 Kelvin. This is colder than expected for micron-sized grains at the comet's distance, suggesting that many grains are larger, 10 microns or more, with thermal inertia that keeps them cooler than the equilibrium temperature. There is also information in the comet's overall brightness and its variation with time. A comet's brightness depends on the amount of dust in its coma, the size of the grains, and the rate at which dust is being produced. By monitoring the brightness over weeks and months, astronomers track the evolution of the dust production rate. For most comets, the production rate peaks near perihelion, when solar heating is strongest, and declines as the comet moves away from the sun. But 3I Atlas shows irregular variations, with production rate increasing and decreasing on timescales of days. This suggests episodic activity, outbursts of dust ejection triggered by local processes on the nucleus. Perhaps the sudden exposure of volatile rich material or the collapse of surface structures weakened by sublimation. The exact mechanism remains unclear. Combining all these observations, spectroscopy, polarimetry, thermal emission. Photometry requires sophisticated modeling. Researchers use radiative transfer codes to simulate how light interacts with dust grains, calculating the scattering, absorption, and emission for grains of different sizes, shapes, and compositions. They run thousands of simulations, varying the parameters, searching for the combination that best matches the observations. The process is computationally intensive, requiring hours or days of processing time on university computing clusters. And even after all this effort, the result is not a single definitive answer, but a range of plausible solutions, each consistent with the data within measurement uncertainties. The final picture that emerges is complex. The swarm around 3I Atlas contains grains ranging from 1/10 of a micron to perhaps 100 microns, with most mass concentrated in grains around 10 microns. The grains are composed primarily of amorphous silicates, coated with organic material and possibly water ice. They are elongated, aligned to some degree, and distributed in a cloud that extends tens of thousands of kilometers from the nucleus. The dust production rate varies irregularly, suggesting episodic activity driven by processes not yet understood. This picture is tentative, subject to revision as new observations become available or as models improve, but it is the best description available given the data at hand. What remains unmeasured, perhaps unmeasurable, is the individual grain. All the observations are averages, ensemble properties of millions or billions of particles. The spectrum shows the average composition. The polarization shows the average shape and alignment. The thermal emission shows the average temperature. No observation resolves a single grain, captures its unique structure, records its particular history. The grains exist only as statistics, as distributions and moments, as abstractions extracted from collective behavior. They are real, physical objects, each one distinct, but they are known only in aggregate, only as population. The universe is full of such ironies, things that exist but cannot be seen, that have properties but cannot be isolated, that matter but remain beyond reach. The shape of a swarm emerges slowly from the data, layer by layer, like a photograph developing in chemical solution. The first images are crude, simple plots of brightness versus distance from the nucleus, showing that dust extends farther than the nucleus itself, that there is a coma, a surrounding cloud. Then come the two-dimensional projections, images taken at different wavelengths that reveal structure within the coma. Brighter regions, dimmer regions, asymmetries that suggest the dust is not distributed uniformly. These images are still projections, collapsing three-dimensional reality onto a flat detector. They show what the swarm looks like from Earth's vantage point, but not its true geometry in space. Reconstructing the three-dimensional structure requires multiple observations from different angles, or observations at different times as the comet's orientation changes. For 3I Atlas, the opportunities are limited. The comet passes through the inner solar system quickly, and most of the time it is oriented such that Earth sees it from roughly the same angle. Only during a few weeks in November 2024, as the comet's trajectory carries it past Earth's orbit, does the viewing geometry change significantly. Observers seize this opportunity, scheduling observations at multiple telescopes, coordinating efforts across time zones and hemispheres. The data they collect is pieced together later, combined with earlier observations, fed into algorithms that invert the two-dimensional images to reconstruct the three-dimensional distribution of dust. The algorithms are based on assumptions. They assume the dust distribution is smooth, that it varies continuously rather than jumping discontinuously from one region to another. They assume the grains scatter light according to known physical laws, that there are no exotic optical effects from unknown materials. They assume the observations are accurate, that the noise is random rather than systematic. With these assumptions, the algorithms produce a model, a mathematical representation of the swarm as a function of position in three-dimensional space. The model can be visualized, rendered as images showing what the swarm would look like from any arbitrary viewpoint. It can be queried, interrogated for properties like total mass or density gradients. But it is still a model, an approximation shaped by assumptions and constraints. The model shows a tail stretching behind the nucleus, pointing away from the sun as expected. The tail is not a thin filament but a broad fan, widest near the nucleus and tapering gradually as it extends outward. At its widest point, the tail spans 30,000 kilometers, roughly twice the diameter of Earth. It extends for at least 100,000 kilometers. Possibly farther, the outer regions are so diffuse that they blend into the background noise, making the boundary between tail and empty space difficult to define. The tail is not uniform. It contains streamers, regions of slightly higher density that run parallel to the tail's axis, separated by gaps of lower density. These streamers suggest that dust is being ejected from discrete sources on the nucleus rather than uniformly from the entire surface. There is also a sunward jet, a feature not predicted by standard cometary models. Most cometary dust is pushed away from the sun by radiation pressure, forming tails that point anti-sunward. But the model of 3i Atlas shows a faint concentration of dust extending toward the sun, a jet that persists for several thousand kilometers before dispersing. This jet cannot be sustained by radiation pressure, which acts in the wrong direction. It must be maintained by some other force, perhaps the momentum of gas escaping from the nucleus, dragging dust particles along with it. Gas can flow in any direction determined by local topography and the orientation of active vents. If a vent on the sunward side of the nucleus is particularly active, it could produce a jet pointing toward the sun, at least temporarily, until rotation carries the vent to a different orientation or until the vent becomes inactive. The model also reveals a halo, a diffuse envelope surrounding the nucleus that extends in all directions, roughly spherical, denser near the center, and thinning gradually outward. The halo contains the smallest grains, those most affected by radiation pressure and least bound by gravity. These grains are pushed outward by sunlight, but not yet fast enough to escape entirely. They linger in the vicinity of the nucleus, forming a cloud that envelops the comet like a fog. The halo's radius is difficult to measure precisely. It depends on how one defines the boundary between halo and background. But estimates place it at around 50,000 kilometers, large enough to contain several Earths side by side. Computer models extend the reconstruction beyond what can be directly observed. By simulating the motion of individual grains under the influence of solar radiation, gravity, and gas drag, researchers predict how the swarm will evolve over time. The simulations start with grains ejected from the nucleus at various velocities and in various directions, then track each grain's trajectory as it responds to forces. The result is a dynamic model, a time-evolving representation of the swarm that can be compared to observations at different dates. The comparison is not perfect. The simulations contain free parameters that must be tuned to match observations, and different choices of parameters produce different predictions. But the simulations provide insight into processes that cannot be observed directly, showing how dust production varies with solar distance and how the swarm's structure changes as the comet moves. One simulation explores what happens if the nucleus fragments. Cometary nuclei are fragile, held together by weak forces that can be disrupted by thermal stress or tidal forces. If the nucleus cracks, releasing a burst of dust and gas, the swarm structure would change dramatically. The simulation shows that fragmentation produces a sudden brightening, followed by a rapid expansion of the dust cloud. The tail becomes broader and more diffuse, the halo grows denser, and new features appear: transient jets and streamers that fade over days as the ejected material disperses. The simulation matches some aspects of the observations, particularly the irregular brightness variations and the extended dust distribution, but it also predicts features not seen in the data, suggesting that if fragmentation occurred, it was minor, releasing only a small fraction of the nucleus's mass. Another simulation tests the interstellar dust hypothesis, the idea that the swarm contains dust accumulated during the comet's journey through space rather than freshly ejected from the nucleus. The simulation tracks grains moving through the interstellar medium, accumulating on the comet's surface through collisions and electrostatic attraction. The result is a swarm that is more extended and less structured than one produced by recent ejection, consistent with some observations. But the simulation also shows that most accumulated dust would be stripped away when the comet enters the inner solar system, swept back by the ram pressure of the solar wind. Only a small fraction would remain, not enough to account for the observed brightness of the swarm. The interstellar dust hypothesis, while intriguing, does not fully explain the observations. The models are tools, not truths. They represent possible explanations, scenarios consistent with the data within their assumptions. They are judged not by whether they are correct, but by how well they predict observations and how much insight they provide into underlying processes. A model that matches all available data but makes no testable predictions is less useful than a model that matches most data and suggests new observations to distinguish between competing hypotheses. The models of 3I Atlas's swarm are in this latter category. They fit the observations reasonably well, and they suggest that future observations, particularly at wavelengths not yet measured or from vantage points not yet accessible, could refine understanding significantly. The swarm's geometry, in the end, is not fixed but fluid. It changes with time, with distance from the Sun, with the activity level of the nucleus. What the models capture is a snapshot, a representation of the swarm's state during a few months in late 2024. By the time the results are published, the swarm has already evolved into something different, its structure changed by forces and processes that continue to act whether observed or not. The geometry exists in the data, frozen at the moment of observation, while the physical swarm moves on, unconcerned with models or reconstructions, following only the laws of physics that govern motion and light. At 26 kilometers per second, even a grain of sand becomes a bullet. This is the velocity of 3I Atlas relative to the Sun, and by extension, relative to any dust or debris lingering in the inner solar system. At this speed, kinetic energy dominates. A grain 1 millimeter across, massing roughly a milligram, carries kinetic energy equivalent to a small firecracker. If it strikes a solid surface, the impact releases this energy in a fraction of a microsecond, vaporizing the grain and excavating a crater many times its own diameter. The surface material melts, then boils, then ionizes into plasma. A flash of light marks the impact, lasting nanoseconds, visible only to instruments designed to detect such transient events. Collisions in space are rare but inevitable. The solar system is not empty. It contains dust from comets, fragments from asteroids, particles shed by the Sun itself. Most of this material orbits in the same direction as the planets, moving at speeds measured in tens of kilometers per second. But 3I Atlas is not orbiting. It is passing through. Its trajectory inclined and retrograde relative to the planetary plane. The relative velocity between the comet and the ambient dust population is therefore higher than for most solar system objects, sometimes exceeding 50 kilometers per second. At such speeds, even micron-sized grains carry enough energy to damage surfaces, to erode materials, to alter the structure of anything they strike. The dust grains in 3I Atlas's swarm collide with each other occasionally. When they do, the outcome depends on the relative velocity and the angle of impact. Head-on collisions, rare but catastrophic, shatter both grains into fragments. The fragments inherit the momentum of the parent grains, scattering in different directions, adding to the population of smaller particles. Glancing collisions, more common, chip off pieces or alter the grain spin states without destroying them entirely. Very gentle collisions, at relative speeds of just meters per second, might allow grains to stick together, forming aggregates held by van der Waals forces and electrostatic attraction. But such gentle collisions are uncommon in the swarm, where most grains move at similar velocities and overtake each other slowly, if at all. Some grains collide with interplanetary dust particles native to the solar system, orbiting the Sun on their own trajectories. These collisions are more energetic, the relative velocity is higher. A grain from 3I Atlas, moving inward at 26 kilometers per second, strikes an interplanetary dust particle moving outward at 10 kilometers per second. The closing speed is 36 kilometers per second. At impact, both grains vaporize, creating a small cloud of hot gas that expands and cools, eventually condensing into a mist of nanometer-sized particles. These secondary particles have no memory of their parent grains. They are freshly formed, born in violence, carrying momentum distributed randomly by the chaos of the collision. They disperse into the solar system, adding to the background population, indistinguishable from dust created by other collisions or by the sublimation of other comets. There is a paradox in these collisions. They destroy individual grains but enrich the medium. Each collision removes 2 grains from the population but creates hundreds or thousands of smaller fragments. Over time, the size distribution of dust in the solar system shifts towards smaller grains, even as the total number of large grains declines. This process, called collisional cascade, operates in any system where objects collide at high velocities, planetary rings, asteroid belts, debris disks around other stars. The equilibrium size distribution follows a power law, with the number of grains increasing steeply as size decreases. Most of the mass remains in large grains, but most of the surface area and most of the number are in small grains. The swarm around 3I Atlas participates in this process during its brief passage through the inner solar system, contributing its own grains to the collisional mix, losing grains to impacts with interplanetary debris. The nucleus itself is also vulnerable. Micrometeorites strike the surface continuously, each impact excavating a tiny crater, ejecting dust and gas, gradually eroding the surface layer. The erosion rate is slow, perhaps a few centimeters per million years, under typical interstellar conditions. But 3I Atlas has been traveling for millions of years, time enough for meters of material to be stripped from the surface. The nucleus that arrives in the inner solar system is smaller than it was when it left its parent star system. The outer layers are gone, sublimated or eroded away, leaving behind the deeper, more refractory core. What observers see is not the pristine comet, but the remnant, the portion resistant enough to survive the journey. Impacts also alter the surface structure. Each micrometeorite impact melts a small volume of material, creating a glassy spot that cools and solidifies. over millions of impacts. The surface becomes covered with these melt spots, a crust of impact-processed material distinct from the underlying pristine ice and rock. This crust is darker than fresh cometary material, its albedo reduced by the mixing of vaporized grains and the creation of carbonaceous residues. The darkness affects the comet's thermal balance, causing it to absorb more sunlight and warm more than a pristine surface would. This, in turn, increases the sublimation rate, accelerating the loss of volatiles and the production of dust. The comet's appearance and behavior are shaped by its history of impacts, by the accumulated damage of millions of years of collisions too small to observe individually but collectively transformative. There is no direct way to measure this impact history. Observers cannot resolve the surface of 3I Atlas, cannot see the craters and melt spots, cannot distinguish processed crust from fresh material. They infer the history from the comet's brightness, from spectral features that indicate surface composition, from models of erosion and sublimation that predict how surfaces evolve under different conditions. The inferences are plausible, but not certain. They depend on assumptions about the interstellar dust density, the comet's velocity, the strength of the surface material. Different assumptions yield different erosion rates, different surface ages, different pictures of the comet's past. What is certain is that the journey has not been gentle. Moving at 26 kilometers per second through a medium containing even one dust grain per cubic kilometer means encountering millions of grains over a journey of parsecs. Each encounter releases energy, erodes mass, changes structure. The comet that arrives in the inner solar system is scarred by this passage, marked by impacts and erosion in ways subtle and profound. It is not pristine, not untouched. It is a survivor, worn by time and distance, carrying the evidence of its travels in its surface and in the dust it sheds. Only took a few million years to cross the galaxy's emptiness and arrive here. Battered, but intact, visible for a few brief months before continuing onward into another emptiness just as vast. What the sun does to strangers is both predictable and violent. Solar radiation arrives as a spectrum visible light, ultraviolet, infrared, each wavelength carrying energy that heats whatever it touches. At Earth's distance, the solar flux measures 1,366 watts per square meter, enough to raise the temperature of exposed surfaces to several hundred Kelvin. Closer to the Sun, at Mercury's orbit, the flux is 11 times stronger. Farther out, at Jupiter's distance, it drops to 1/25 Earth's value. The dust grains surrounding 3I Atlas experience this changing flux as the comet approaches perihelion and then recedes, warming and cooling in response to their changing distance from the Sun. Warming causes sublimation. Ice does not melt in the vacuum of space, it transitions directly from solid to vapor, the molecules escaping the surface when they acquire enough thermal energy to overcome the binding forces holding them in the lattice. Water ice begins sublimating at temperatures around 150 Kelvin, corresponding to distances beyond the asteroid belt, closer to the Sun. Sublimation accelerates, the rate increasing exponentially with temperature. At perihelion, where 3I Atlas passes within 2 astronomical units of the Sun, surface temperatures on sunlit grains exceed 200 Kelvin. At this temperature, water ice sublimates vigorously, carrying away not just water molecules, but also dust particles embedded in the ice, liberating them into space. The sublimation is selective. Water ice, the most abundant volatile in most comets, sublimates first. Carbon monoxide and carbon dioxide, more volatile than water, begin sublimating at greater distances at temperatures as low as 70 Kelvin. Methane and nitrogen are more volatile still. escaping at temperatures below 50 Kelvin. By the time the comet reaches the inner solar system, these hypervolatiles are already depleted from the surface layers. Sublimated during the approach phase when the comet was still far from the sun, what remains is water ice mixed with refractory dust silicates and organics that do not sublimate at all but simply become exposed as the ice around them vaporizes. The dust particles themselves fragment under solar heating. Thermal stress arises from temperature gradients. The sunlit side of a grain warms faster than the shadowed side, creating differential expansion that generates internal stress. If the stress exceeds the material's tensile strength, the grain cracks. Cracks propagate through the grain, splitting it into smaller pieces. The fragments drift apart, each one now an independent particle following its own trajectory. Fragmentation increases the surface area to volume ratio of the dust population, creating more small grains and fewer large ones. It also creates fresh surfaces, exposing material that was previously buried in grain interiors, material that may have different composition or structure than the weathered exteriors. Ultraviolet radiation, the highest energy component of sunlight, breaks chemical bonds. Organic molecules, particularly those containing carbon-hydrogen or carbon-carbon bonds, absorb ultraviolet photons and dissociate into radicals and smaller molecules. This process, called photodissociation, gradually destroys complex organics, converting them into simpler compounds: carbon monoxide, carbon dioxide, methane, hydrogen cyanide. The products sublimate or remain on the grain surface as a carbonaceous residue, darker and less reflective than the original material. Over time, grains exposed to intense ultraviolet become coated with this residue, a layer of refractory carbon that changes their optical properties and thermal behavior. Solar wind also interacts with the dust, though more subtly than radiation. The wind is a stream of charged particles, protons, electrons, helium nuclei flowing outward from the sun's corona at speeds of several hundred kilometers per second. When these particles strike a dust grain, they deposit charge, gradually altering the grain's electric potential. A grain that accumulates a net positive charge repels incoming protons, slowing the charging process. Electrons, lighter and faster, are captured more easily, and over time, most grains acquire a slight negative charge. This charge affects how the grains interact with the sun's magnetic field, causing them to drift along field lines rather than moving in straight lines determined solely by gravity and radiation pressure. The combination of heating, sublimation, fragmentation, and irradiation transforms the dust. Grains that begin their journey as icy aggregates, mixtures of ice and refractory material held together by weak bonds, become desiccated skeletons, the ice gone, only the refractory framework remaining. These skeletons are fragile, prone to further fragmentation, easily disrupted by collisions or thermal stress. They are also darker, their albedo reduced by the loss of reflective ice and the accumulation of carbonaceous residues. A swarm that was relatively bright when far from the sun darkens as it approaches perihelion, not because the grains disappear, but because they change, their surfaces altered by solar processes. There is a mystery in the survival of ice. Spectroscopic observations of 3I Atlas show water emission even when the comet is close to the sun, indicating that ice is still sublimating from surfaces. But simple thermal models predict that all surface ice should be gone by this point, sublimated during the approach phase or rapidly desiccated once the comet enters the inner solar system. The persistence of water emission suggests that ice is being replenished from deeper layers, either through the cracking of surface crusts that expose fresh material or through the migration of water vapor from the interior to the surface. where it recondenses in shaded regions before sublimating again. Both mechanisms are possible. Neither is confirmed. Another mystery is the comet's activity pattern. Most comets show peak activity at perihelion, when solar heating is strongest. But 3I Atlas shows significant activity well before perihelion and continues to show activity long after, when it has cooled and receded beyond Mars's orbit. This suggests that the nucleus contains volatiles more abundant or more easily released than in typical solar system comets. Perhaps the structure is unusually porous, allowing vapor to escape from deep within the nucleus rather than being trapped beneath an insulating crust. Perhaps the composition is different, richer in carbon monoxide or other volatiles that sublimate at lower temperatures. Or perhaps the nucleus is slowly disintegrating, its structure weakened by thermal stress and tidal forces, releasing material not through sublimation alone, but through mechanical breakup. What the sun does to strangers, ultimately, is reveal them. The dust that was invisible in interstellar space becomes luminous when illuminated. The ice that was stable in the cold darkness begins to sublimate, releasing gas and particles. The structure that was preserved for millions of years begins to erode, its integrity challenged by forces absent in the void. The comet does not resist these changes. It simply responds passively. According to the physics of matter and energy, the sun strips away layers, exposes interiors, transforms surfaces. It does this to everything that comes close enough. Asteroids darken, comets outgas, dust grains fragment. The sun is not hostile. It is simply intense, concentrated energy in a region where most objects have evolved under gentler conditions. The strangers adapt or erode. Most erode. The question of where it came from has no simple answer. Trajectory analysis can trace the path backward, projecting the comet's motion into the past, following the gravitational deflections imposed by the sun and planets, working backward through time to determine where the object was 1,000 years ago, 10,000 years ago, 1,000,000 years ago. The analysis shows that 3I Atlas entered the solar system from a specific direction from the constellation Ursa Major, from a region of sky about 30 degrees above the ecliptic plane. The trajectory is hyperbolic, meaning the comet arrived with excess velocity, more than enough to escape the sun's gravity well. This excess velocity, combined with the trajectory's orientation, points back toward a source region somewhere in that general direction. But general direction is not a specific star system. Space is vast. A line drawn backward from the comet's trajectory passes through a volume containing thousands of stars, any one of which might have been the origin point, and the uncertainty grows with distance. Perturbations from other stars, gravitational nudges accumulated over millions of years, deflect the trajectory by small amounts that compound over time. After 10 million years, the positional uncertainty is measured in parsecs. After 100 million years, it becomes meaningless to speak of a specific origin point. The comet came from somewhere, but from where exactly remains indeterminate. Astronomers narrow the possibilities using statistical arguments. Stars within 10 parsecs are catalogued, their positions and velocities known. The analysis asks which of these stars has a trajectory that, traced backward in time, intersects the comet's trajectory within the expected uncertainties. A few candidates emerge. One is a red dwarf 8 parsecs away, moving through space at a velocity that would place it near the comet's position several million years ago. Another is a binary system 12 parsecs distant, its orbital dynamics creating opportunities for planets or comets to be ejected at high velocities. A third is a young star cluster 15 parsecs away, its gravitational interactions potentially scattering objects into interstellar space. None of these candidates is definitive. Each has a probability, a likelihood based on distance, velocity, and the dynamics of ejection. The probabilities sum to less than 1, meaning there is a significant chance the true origin lies among stars not considered, stars farther away or less well characterized or simply overlooked. The chemical composition of the dust provides additional constraints. If the comet formed around a star with a different metallicity than the Sun, a different abundance of elements heavier than helium, the dust should show corresponding differences in trace element ratios. Some elements, like magnesium and iron, are produced by different types of supernovae and in different proportions depending on the star's mass and age. By measuring these ratios in the dust and comparing them to the known metallicity of candidate stars, astronomers can rule out some origins and favor others, but the measurements are noisy. The differences are subtle, and the conclusions remain tentative. The data suggests that 3I Atlas formed in a region with slightly higher metallicity than the Sun's neighborhood, consistent with formation in a younger stellar population or closer to the galactic plane where metal-rich gas is more common. This narrows the candidates but does not identify a single star. There is also the question of how the comet was ejected. Comets do not leave their parent star system spontaneously. They require a gravitational perturbation strong enough to accelerate them beyond escape velocity, a close encounter with a planet, a passing star, or the dynamical chaos of a multiple star system. Most stars are part of binary or multiple systems, their gravitational interactions creating opportunities for such ejections. A comet orbiting in the outer reaches of a binary system might be perturbed by the companion star, its orbit stretched and tilted until one perihelion passage brings it close enough to one of the stars to be flung outward. The velocity at ejection depends on how close the comet passes to the star. For 3I Atlas, the observed velocity suggests an ejection event that brought it within a few astronomical units of a solar mass star, close enough for gravitational acceleration, but not so close as to disrupt the nucleus. The timing of ejection is also uncertain. If the comet left its parent system 1 million years ago, it must have originated within about 30 parsecs, given its velocity. If it left 10 million years ago, the origin could be several hundred parsecs distant. The chemical and isotopic data, which show some processing and aging, favor a longer journey, multiple millions of years at least. But this conclusion is indirect, based on models of cosmic ray exposure and surface erosion rather than direct measurement. The uncertainty is large, spanning an order of magnitude or more. One hypothesis suggests the comet originated not from a single star, but from an interstellar cloud, a molecular cloud where stars are currently forming. In such environments, comets could form in the outer regions of protoplanetary disks and then be ejected by dynamical interactions before their parent stars fully ignite. These objects would never have experienced strong stellar heating, remaining pristine, their surfaces unprocessed. The chemical signatures of 3I Atlas show some consistency with this scenario, though they also show signs of heating and alteration that suggest at least brief exposure to a stellar environment. The cloud hypothesis remains speculative, difficult to test without better knowledge of the comet's age and thermal history. Another intriguing detail comes from the comet's spin. The rotation period, measured from brightness variations as the nucleus spins, is about 16 hours. This is relatively slow for a comet. Most comets rotate with periods of a few hours. Their spin rates increased by outgassing torques and collisions. A slow spin suggests either that the nucleus is large and massive, resistant to torques, or that it has been spun down by some dissipative process. One possibility is that the comet experienced a collision during its journey, an impact that transferred angular momentum and slowed the spin. Another is that the comet is a fragment of a larger body, broken apart by tidal forces during a close stellar encounter. Fragments typically spin slower than intact bodies, their angular momentum distributed differently. The data does not distinguish between these scenarios, but the slow spin hints at a complex history. The trajectory also reveals that 3I Atlas will not visit any other star system soon. Projected forward in time, the comet continues outward from the Sun, its velocity gradually decreasing as the Sun's gravity slows it. But the deceleration is small, insufficient to capture the comet into a bound orbit. In 1,000 years, 3I Atlas will be beyond the heliopause, the boundary where solar influence fades. In 10,000 years, it will be a light year from the Sun, moving through the local interstellar medium at 25 kilometers per second. In 1,000,000 years, it might pass near another star, deflected slightly by that star's gravity, its trajectory altered by a few degrees. But there is no obvious next destination, no star that lies directly along its path. The comet drifts, moving through the galaxy, a wanderer with no home, no orbit, no return. Where it came from remains a question of probabilities and uncertainties, of candidates and constraints, of chemical hints and dynamical possibilities. The answer is not a single star, but a region, a population, a class of environments where comets form and from which they are occasionally ejected. The comet carries the signature of that environment in its dust and ice, in the isotopes and organics that record formation conditions. But the signature is not unique. It describes a type of place, not a specific location. The comet came from somewhere out there, from a star system that may no longer exist or may have changed beyond recognition in the millions of years since the ejection. The origin is distant, both in space and in time. Receding into uncertainty, the farther back one traces the trajectory. Other visitors we have not seen yet drift through the solar system undetected, passing between planets, crossing orbits, continuing onward without leaving any record of their passage. This is not speculation, but statistics. Calculations based on the frequency of detected interstellar objects suggest that the actual population is far larger than what has been observed. For every object bright enough and close enough to be noticed by automated surveys, hundreds or thousands pass too far away, too small, or too fast to register. They move through the system in silence, invisible to instruments, unknown to catalogs. Their existence inferred only from models of galactic dynamics and the formation rates of planetary systems. The detection of 3I Atlas was fortunate. The comet passed within 2 astronomical units of Earth, close enough that its brightness exceeded the detection threshold of several survey telescopes. It also arrived at a time when surveys were operating, when the sky was being monitored continuously by automated systems designed to detect moving objects. A decade earlier, before these surveys existed, the comet would have gone unnoticed. A century earlier, it would have been invisible, perhaps glimpsed as a faint smudge by a careful observer, but attributed to a distant galaxy or dismissed as instrumental noise. The window of detectability is narrow, constrained by technology and observing conditions, and most interstellar objects pass outside this window. The rate of interstellar visitors can be estimated from first principles. The Milky Way contains roughly 200 billion stars, a typical planetary system. Based on what is known from solar system dynamics and observations of exoplanets, ejects comets and asteroids at a rate of perhaps 1 per million years. Most ejections occur during the early phases of planet formation, when gravitational interactions are strongest and orbits are still unstable. Some ejections happen later, triggered by passing stars or by the gradual evolution of planetary orbits. Multiplying the number of stars by the ejection rate gives a galactic production rate of hundreds of thousands of interstellar objects ejected per year. These objects disperse through the galaxy, moving at velocities of tens of kilometers per second, filling the interstellar medium with a diffuse population of wanderers. The density of this population, averaged over the galaxy, is low. One estimate suggests roughly 1 interstellar object per cubic astronomical unit within a few hundred parsecs of the Sun. This translates to millions of objects within the volume of space that defines the solar system, but most are too small to detect. Only the largest objects kilometers across or larger reflect enough sunlight to be visible at interstellar distances. Smaller objects, the comets and asteroids that dominate by number, remain dark, detectable only if they pass very close to the Sun and become active, producing dust and gas that scatter light. Some of these objects may have already passed through without detection. Before 2017, when Oumuamua was discovered and identified as the first confirmed interstellar object, astronomers were not looking for such visitors. Surveys focused on solar system objects, asteroids and comets in bound orbits, near-Earth objects that might pose collision hazards. An object on a hyperbolic trajectory, moving through the system once and never returning, would have been classified as anomalous, perhaps misidentified as a long-period comet or simply ignored as a data artifact. It is possible that interstellar objects appeared in archival data from older surveys, their hyperbolic orbits unrecognized, their true nature missed. The discovery of Oumuamua and 2I Borisov, the second confirmed interstellar object, changed this. Astronomers now actively search for hyperbolic trajectories, for objects with velocities too high to be bound to the Sun. Survey software has been updated to flag such objects, and follow-up observations are prioritized to determine orbits before the objects fade from view. Despite these efforts, only a handful of candidates have been identified and only 3 confirmed. The detection rate suggests that interstellar objects pass through the inner solar system within Jupiter's orbit at a rate of a few per year. Most go undetected, their trajectories carrying them through regions of space that are not being monitored, or at times when telescopes are pointed elsewhere. There is also the population of interstellar dust grains not bound to any larger body, traveling independently through the galaxy. These grains are smaller than the dust around 3 Atlas, typically a tenth of a micron or less, too small to produce detectable scattered light. But they are numerous, and they carry momentum. Spacecraft in the outer solar system have detected impacts from interstellar dust, tiny particles striking at velocities high enough to vaporize themselves and small portions of the spacecraft's surface. The impact rate is low, a few particles per square meter per year, but it confirms that the solar system is constantly being bombarded by material from beyond. A steady influx of dust that adds to the local population and mixes with solar system debris. Some of these dust grains are captured by the Sun's gravity, spiraling inward as radiation pressure and gravitational forces balance. Others pass through without deflection, their trajectories barely perturbed by the Sun's influence. A fraction collide with planets, contributing to the slow accretion of mass that all planetary bodies experience. Earth intercepts a small amount of interstellar dust each year, perhaps a few tons spread over the planet's entire surface. This dust settles into the atmosphere, becomes incorporated into ocean sediments, or is collected by high-altitude research aircraft equipped with sticky collectors designed to capture micrometeorites. Analysis of these particles reveals their interstellar origin through isotopic signatures that do not match solar system materials. The visitors we have not seen include not just small objects but also large ones. Rogue planets, worlds ejected from their parent star systems and now drifting through the galaxy, are predicted to exist in large numbers. Some models suggest that there are more rogue planets than stars, a vast population of dark, cold worlds moving through the interstellar medium at velocities determined by their ejection events. These planets are nearly impossible to detect unless they pass very close to the Sun or emit detectable thermal radiation in the infrared. One rogue planet may have passed through the solar system in recorded history, its gravitational influence perturbing comets or asteroids without being recognized as a distinct object. There is no definitive evidence for such a passage, but the statistics suggest it is not implausible. The mystery of undetected visitors is also a mystery of bias. Surveys find what they are designed to find: objects that are bright, that move at predictable speeds, that appear in regions of sky where telescopes are pointed. Objects that fall outside these criteria remain invisible. An interstellar object moving perpendicular to the ecliptic plane, passing over the solar system's north pole, would spend little time in the regions most intensively surveyed. An object with very low albedo, reflecting almost no sunlight, would be detectable only at very close distances. An object moving faster than expected, at 50 or 100 kilometers per second, might be dismissed by automated software as a data error. The population of interstellar visitors is shaped by what can be detected, and what can be detected is a small, biased sample of what exists. Future surveys, with larger telescopes and more sophisticated algorithms, will detect more interstellar objects. The Vera Rubin Observatory, scheduled to begin operations soon, will survey the entire southern sky every few nights, detecting objects hundreds of times fainter than current surveys. It is expected to discover dozens of interstellar objects per year, enough to characterize the population statistically and to identify unusual members objects with extreme velocities, unusual compositions, or orbits that trace back to nearby star systems. These discoveries will refine estimates of ejection rates and population densities, will provide more examples to compare with 3i Atlas, will reveal whether this comet is typical or exceptional. Until then, the visitors continue to pass unseen. They move through the dark spaces between planets, through the asteroid belt and the Kuiper belt, across the heliopause and into the